So for the next talk, we have David Blei on deep exponential families.
Okay, thanks, Chris. Thanks very much. Thanks to the organizers for inviting me. I'm Dave Blei from Columbia, and I'm going to talk about deep exponential families. You can't hear me, Dan? Now this is better. Okay. I'm going to lean in. This is joint work with Rajesh Ranganath, Limpeng Tang, and Laurent Charlin. And as Neil Lawrence said, it's nice to be in the small, intimate NIPS workshop environment. Okay, this workshop's about Bayesian deep learning. What is deep learning? I'm not an expert in deep learning, but I like this paper by Bengio and Courville and Vincent from 2013, and I think deep learning has to do with learning layered representations of high-dimensional data. Okay, so that's going to be deep learning. What is Bayesian statistics? As Neil Lawrence pointed out, the definition of Bayesian statistics is up for debate. But one working definition is that Bayesian statistics casts all inferences of unknown quantities as probability calculations. Bayesian inference then involves the conditional distribution given the observations, which we call the posterior. Okay, that's the consequence of asserting that all inferences about unknown quantities should be made as probability calculations. And if you want to read about Bayesian statistics, there's many great places to read about that field, but Bernardo and Smith 1994 is a nice book about the theory of Bayesian statistics, and Bayesian data analysis from 1995, Gelman et al., is a great book about the applied side of the statistical perspective on Bayesian statistics. Of course, we have Bishop and Murphy and Kohler and Friedman here in the machine learning world to understand probability modeling and Bayesian statistics that way. Okay, so what is Bayesian deep learning? Well, that's what we're here to think about together. Given deep learning and Bayesian statistics, those definitions, one way you can think about Bayesian deep learning is to do posterior inference of layered representations of high-dimensional data. And so what I want to talk about today is some work that we've done on what are called deep exponential families. And this is the graphical model that I'll be discussing during this talk. So you can meditate on it for a little bit. Basically, it's going to be hard. I want to point. Let me see. Does this work? No. Okay. Oh, can you see that cursor? Yeah? All right, cool. Okay, so this is going to be the graphical model. These are called deep exponential families, and we're going to try to learn layered representations of high-dimensional data using Bayesian statistics. And the idea is that our data are x, okay? X, N, I. I is the dimension, xn is the data, and n is the data point. And the idea is that we have high-dimensional data, so x and I ranges from 1 to v, and v is very high. And this data point comes from an exponential family with a natural parameter that is a link function that's called g, of a dot product of some weights called w0 here at the observation level, and some hidden variables z. Okay, so z and 1 are the first, oops, sorry about that. Z and 1 is the first layer of the hidden variables. Okay, so there's some hidden variables one layer up from the observation, and we take the dot product of those hidden variables and some weights. That gives us a quantity, put it through a link function. Let's make the identity link function for now, just for kicks. Just make that quantity the natural parameter of some exponential family, and then we draw x and I from that exponential family. So it could be a gamma, could be a Gaussian, could be a categorical, could be a whatever. We're going to draw the value from the corresponding exponential family. Okay, so what I just described, of course, is probabilistic PCA, right? Exponential family PCA, Mohammed and Heller and Garamani. But now what we're going to do is we're going to take those z's. Where did those z's come from? Those hidden variables. Well, they came from the same kind of architecture, right? The same kind of probabilistic architecture, where z then comes from a layer above it, an exponential family with some weights and some hidden variables on top of it. And so you can see here, and this goes L layers up. So you can see here in the middle, I've illustrated just something in the middle of this stack of latent variables. We have the elf latent variables come from an exponential family with their corresponding weights at layer L, and the hidden variables above it. Okay, and so this is a graphical model that, in its posterior, conditioned on X, learns a latent representation of high-dimensional data. Each data point is associated with a stack of vectors of latent variables, and each layer is associated with some weights which interact with that stack to generate the data. Okay, if you read this going down, then you start with some latent variables, generate the next layer of latent variables, the next layer of latent variables, the next layer of latent variables, and so on, until you finally bottom out at the data, which maybe is how I should have described it from the beginning. Okay, so as I mentioned, each distribution is in an exponential family. Okay, so we're going to put them in their canonical exponential family form. So here you can see an example. This is the probability of the elf latent variable at dimension k, conditional on all of the latent variables above it and the corresponding weights. And you can see I've written that as an exponential family here with natural parameter eta, sufficient statistics t, and log normalizer a, where eta, the natural parameter, as I mentioned, is this link function applied to the dot product. Now, the inner product inside the link function is not strictly necessary, although those are the kinds of deep exponential families that we've explored. Okay, so what can we do with this? Well, as I mentioned, the data comes from an exponential family, so the data could be categorical or real or positive or whatever. But of course, now these latent variables also come from an exponential family. So if we want non-negative latent variables and sparse latent variables, we might use a gamma. If we want binary latent variables, we could use a Bernoulli. And I'm sure many of you are thinking of the related work that these imply. I'll mention that in a bit. If we want count latent variables, we could use a Poisson. We could use real valued latent variables. We use a Gaussian. And each of these instantiates a different type of deep exponential family. We know that one of the benefits of neural nets are these nonlinearities between the hidden layers that let us capture rich patterns in the data sets. And nonlinearities arise naturally here. There are really two sources of nonlinearity. So by nonlinearity, I mean the relationship between the expectation of a lower layer conditional on the layer above it. Okay, so here we see that the elf layer comes from an exponential family with its natural parameter. Now, the expectation of ZNLK, right? That's that's our idea of what its value might be. Where does that come from? Well, it combines the weights W, I'm pointing to this with the cursor here, it combines the weights W here, the previous layer ZNL plus 1, and those get combined into G. So one source of nonlinearity in that expectation is G, right? Whatever we choose our link function to be. But then, to remind you, in an exponential family, the expectation of a variable that's distributed by an exponential family is the gradient of that log normalizer, right? That gives us the expectation. And if you don't know that fact, it's a beautiful fact. It's worth either reminding yourself or learning it by looking in a book like Bishop or Murphy's book. Anyway, take the gradient of the log normalizer, and that gives us the expected value of z. Now, that gradient induces another nonlinearity. So conditional on the layer above, the expectation of z is some nonlinear function of the layer above, and that nonlinearity comes from both g, but also from the exponential family that we've assumed, i.e. the fact that we have to take the gradient of the log normalizer to get that expectation. Okay, so for example, when z is a Bernoulli, then the gradient of a is the sigmoid function. Okay, so this recovers a sigmoid belief net in that way. There's a lot of related work. Whenever, at every NIPS workshop talk, when there's a related work slide, someone makes a joke that they forgot some people and they should just email them if they're mad that they got forgotten. So I'm making that joke. you know, a lot of these papers Zubin mentioned in his beautiful talk on the history of Bayesian neural networks. These are especially Neil 1990 on stochastic feed-forward networks and the subsequent work, the newer work on deep latent Gaussian models. And this is in some sense, you know, the exponential family harmoniums from Welling, that was the exponential family characterization of undirected neural nets, and this is the directed model version. Recently, Mingyuan, Zhu, and others have worked on gamma belief nets and Poisson belief nets that are instances of these exponential family, deep exponential families. And then, so that's in the kind of neural net deep learning literature. The kinds of work that this relates to in statistics are generalized linear models. So we're generalized linear models, of course, are exponential family generalizations of things like regression, and we're doing the same thing here for unsupervised feed-forward networks. In one layer, this is basically probabilistic PCA or exponential family PCA, or Bayesian non-negative matrix factorization. Okay, and again, if please email me if you feel that I should cite something else here that I have not cited. Okay, so as a running example, we're going to look at high-dimensional discrete data, where x and I is a count. All right, so this was a count, for example, of word I in document n. And we're going to use a Poisson likelihood. All right, so x and I comes from a Poisson whose rate is g of some inner product of the weight for that word and the latent variable for this document. So every document now is associated with a stack of latent variables, and then that's the bottom layer of that stack of latent variables combines with the different W's to create counts for each possible word in the vocabulary. Okay, so that's going to be the likelihood model. That's at the bottom. But what could we do for this stack of latent variables? Well, one is a Bernoulli def. Okay, this is the original sigmoid belief network, where the z's are all Bernoulli. The link function g is the identity, and we put a Gaussian prior on the weights. Now, in this case, the expectation, as I mentioned, comes from the logistic function, logistic of a dot product of z and w. And the variable, if you want to interpret these hidden variables along the way, represent whether or not a particular component is on to create this document. Okay, we could go beyond the sigmoid belief network and think about a Poisson def. Right? So now again, we'll use the identity link, a Gaussian prior on the weights, and the expectation is the exponentiated dot product. Right? The expectation of a particular latent variable here is the x of the dot product of z and the weights, the previous layer z and the weights. Okay, and so here, whereas in the Bernoulli def, the z represented whether or not a component is on, here z represents the amount that component is on, and that amount is a positive integer. Okay, we could change the link function. We use the log link, and that changes the expectation of z. Right now, z's expectation is exactly the dot product between z and w. Okay, and here we need w to be positive, so we place a gamma prior on w. Okay, we call that log link Poisson def. Okay, perhaps most interesting is a sparse gamma def. This is another kind of def we can define. You can recall that the gamma is a two-parameter distribution on the positive reals. It's an exponential family distribution with sufficient statistics z and log z, and when one of the parameters, alpha, is smaller than 1, the mass concentrates around 0. Okay, so there's deep connections between gammas and Dirichlet's and Bayesian nonparametrics to get these kind of sparse representations of distributions. Sorry, not sparse, sparse distributions that place their mass on just a small part of the support. And when alpha is less than 1, that's what you get. You draw many, many, many gammas with alpha less than 1. Many of them will be close to 0, and a few of them will be spiked much higher. That's kind of the core idea behind Bayesian nonparametrics and random measures. So here, we're going to use sparse gammas for these z's. Remember, these z's are vectors of latent variables, and so if we use sparse gammas, then some of those z's are going to be active for different data points, and some of them are going to be, and most of them are going to be close to 0. And the way we parameterize that is with this link function, where the shape parameter is does not depend on the previous layer, but the scale or the rate depends on the previous layer. In particular, it's alpha over z transpose w. I'll admit I forgot whether this is called the scale or the rate. I always get those confused. Again, W needs to be positive, so we place a gamma prior on W, and in this little model, the expected value of Z is, again, the dot product, as it was in the Poisson link case, okay? But these are going to be sparse. So, for example, with different activation levels, activation 0.1, it's going to be very sparse. Many of these latent variables are going to be close to 0. With activation 1, it's going to be less sparse, and with activation 10, it'll be less sparse still. Okay, so what just happened? Well, I put up that graphical model and asked you to meditate about it. We set the likelihood of the graphical model to be a bank of Poisson distributions, right? One for each word. So we have a bunch of word counts. And then we describe different methods, different exponential families for these layers of hidden variables that go above it. All right? With one layer, this is simply probabilistic PCA or exponential family PCA. But now we're stacking those exponential family PCAs one on top of another to kind of simulate these deep architectures that we see to learn layered representations in an unsupervised way. Okay? Of course, the goal is to do inference. How do I condition on X and infer both the weights that govern the whole data set and the per data point latent variables, this cascade of Z variables. All right, so our goal is going to be to try out many defs on a data set. We want to explore the different exponential family distributions on Z. We want to explore different link functions. We want to explore number of layers and of course, the dimension, the number of components in each layer. And if we were going to do this and derive a new algorithm every time we needed to do this, it would be very difficult. So our solution is to use black box variational inference. Okay, that's Ranganath and others from 2014, where we take Monte Carlo gradients of the variational objective functions. We're doing variational inference. We're minimizing the Kale divergence between an approximating family and the exact posterior, P of Z and W, given the data. And we are going to do that with Monte Carlo gradients that are generic in the sense that even changing the model, we don't really need to change our algorithm that much. Once we specify the model, we have a good variational inference algorithm. The whole idea behind black box variational inference is to be able to, look at many, many models with one algorithm. And recently, Rajesh and Dustin Tran and I have worked on hierarchical variational models, which is a better solution to doing inference on defs. And that's from 2016. So look up those papers if you're interested in the algorithms. With these algorithms, we can explore many defs. And so we took two corpora, New York Times and Science. Each is about 150,000 documents with a vocabulary of 7,000 words. And we evaluated document prediction perplexity. It's a measure of model fitness. And used black box variational inference for all runs. All right, so we had one code base, and all we do is we vary the depth and the distributions and the link functions for these deep exponential families. Let me go back to the graphical model, just because I like it. So again, now the X is a set of word counts for a New York Times article. There's 7,000 vocabulary terms, and we're using black box variational inference to infer all of these hidden variables to represent that big collection of New York Times articles. Okay, so here's a big table of numbers. You don't need to read the table. The point is that with that one algorithm, we were able to explore many, many different types of defs. Okay, explore sigmoid belief networks, Poisson defs, change the link function of the Poisson, change the numbers of layers, use sparse gammas, and so on. Change the prior on W. And the def representations of the documents do better than things like LDA, latent theoretically allocation, and DocNate. Okay? This cost us $40,000 on Amazon. It was the most expensive AI stats paper. Okay. We can also represent we can look at what do we get out of the defs with LDA and things like that? We get topics. So out of the defs, we also get a representation that might be worth interpreting. I don't know if you can see this. So this is from the New York Times. This is just a part of the picture. And basically, so what's happened is these Z's connect to each other in a sparse way. I think this is the sparse gamma def. And so some Z's at a lower level will depend on Z's at a higher level, but they might not depend on other Z's at that high level, right? Because the Z is a vector. And so when we looked at this, at the bottom level, the Z's, of course, tell us which words are going to have high counts when that Z is on. And so we found these topic-like things about courts and police and about government and about political parties. Well, sorry, I'm using the thing we learned above. About courts and police, about schools and education and election campaigns and so on. But then those, when they're active, those are active via patterns from the layer above. And above, we then see that they are connected in ways that make sense. And the way we interpreted this is through things like the judicial, legislative, and executive branches of the government, political parties, and then media and religion. All right, and then above that, we saw a separation between government, the main government topics, and politics. And so you get this nice hierarchical structure out of and Zubin mentioned hierarchical models as a way to connect deep learning and Bayes. You get this nice hierarchical structure from interpreting these latent variables. Okay, why are we doing this? Why do we care about Bayesian deep learning? Well, Bayesian methods, as you know, are modular and reusable. Right? We like graphical models because when we work on one graphical model, we can then plug it into a more complicated graphical model and use the results from our inference. And so we can place defs in the context of more complicated models. And so I want to quickly give you two examples, although he showed me 5 minutes, like more than 5 minutes ago. Is that right? Okay, it's time. 3 minutes, good, okay. So it's generous. So I'm going to show you two things, double defs for recommendation and then deep survival analysis for medical risk assessment. Okay, this is, what we could fit this model over and over again, but the idea is to embed it in more complicated models. All right, so recommendation, I think you're all familiar. We have users and books in this case, and users read books and they decide whether or not they like them. And in the classic matrix factorization solution to that problem, we associate each user with a vector of preferences, theta I, and we associate each item with a vector of attributes, beta j, and then the rating, whether or not user I liked item j, is some function of the dot product of that user's preferences and the item attributes. Okay, so here's a picture of that. And what we can do then is we can put def priors on user preferences and item attributes. So now the item attributes are going to have a complicated correlation structure, and the user preferences are going to have a complicated correlation structure. And then the bottom values there, which was x in that other graphical model, but here is actually something latent, are combined in a dot product to create the interaction between the user and the item. Okay, that's yij. Okay, again, a table of numbers says that compared to something like Gaussian matrix factorization, the classical solution to this problem, having a multi-layer representation of these latent variables gives us predictive power. Okay, last example is survival analysis. Survival analysis measures time to an event. All right, so this might be the time until your car breaks, the time until you, hope it doesn't happen, you have a heart attack or something happens to your heart. Rajesh put the movie picture there. I don't understand. I think we all know when the movies are going to start, but maybe it's the time until you walk out of a movie because it's so bad. Okay? Again, so survival analysis is a cornerstone of diagnosing risk, of understanding when you go to the hospital, what risk you have for different conditions. And again, we can embed the def into a survival analysis model. I won't go into the details, but you can look at this paper from this year at the conference on medical informatics and machine learning. And again, compared to the existing methods for doing survival analysis, the def gives us a lot of predictive performance. Okay, in my last -1 minute, I wanted to mention two other Bayesian deep learning projects that have been going on in my group. One is exponential family embeddings, which just as we generalized deep networks here to exponential families, this generalizes the idea of word embeddings to exponential families, so you can embed other types of data. And the other is Edward, which Dustin already, I didn't know he was going to do that, gave a nice spotlight on Edward, so I don't need to say much about that, but Edward is a software library for modeling, inference, and criticism. Good. Thank you very much. Yeah. Or I don't. It looks like there's a question there and a question there.
Very nice talk. Thank you very much. Before I start using your method, could you give a little bit more detail on the variational distribution that you use to estimate to get these results?
Sure. Oh, they don't need a slide. So The black box variational inference idea, the idea is this. We've got the posterior we want, P of z given x, and we're going to use a mean field approximation. And the issue, I mean, in some sense, defs were defined in 1990 by Radford-Neal's paper, but the issue was we couldn't do inference in them, right? And so what black box variational inference does is it turns that inference problem into a stochastic optimization problem, and then it uses Monte Carlo gradients of the objective, of the elbow, the KL divergence, something up to a constant equal to the KL divergence. And those Monte Carlo estimates don't require difficult to compute calculations about Q or P. And so that's how inference works. I can point you to that paper, or we can talk offline. I can give you the details.
So it's a factorized. It is
fully factorized, yes. However, as I mentioned, hierarchical variational models is a new way of doing variational inference that works better for defs. And there, it is not fully factorized. There we are using a structured variational approximation.
Can you not use the exponential family idea for the variational distribution?
The variational distributions are still in the exponential family. They are, yep. But, you know, again, it's like the separation of models and inference that we've been talking about, where the model has exponential families and we exploit them everywhere in the model. Variational approximation, we can do other things if we want to.
Thank you.
Yep, thanks.
Is there time for another question? I don't know.
Well,
Anyway.
So I'm always interested in what Neil has to say. So.
Right.
Those guys were queuing first. I feel bad. But
I'm going to go for it anyway.
All right.
So how much do you...
I thought he was saying we don't have time for another question. Yeah, please, go ahead.
So how much do you actually gain from treating the weights as like in a Bayesian way, as opposed to not treating them in a Bayesian way? Is there any uncertainty left in your, once you do the variational inference, is the field not zero at this number of data points that you fit it to?
That's a good question. I can't really answer it without looking at the actual fits, which I don't have at my fingertips right now. But that question is partly about why do Bayesian statistics, and one reason has to do with perhaps the posterior uncertainties are useful to you. Another reason is that there is regularization involved when you use variational inference in a Bayesian model, and so the predictive performance could be better even if we didn't care so much about the posterior uncertainty. Yeah. Question?
So a quick thought was that I guess if the inverse link functions are ReLUs and you use the Gaussian model, and then your top layer you make it an input fixed layer, and the output you make it a classification label, then you basically have a deep neural network that you're treating in a Bayesian way. Have you tried running that structure, and how well does it do compared to other Bayesian approaches? Because what I'm saying is deep neural nets are also a subclass of your approach, I suppose.
Right. We haven't tried that, but it's true. Once you see the def, everything looks like a def.
Hi there.
I just wanted to answer that.
Oh,
So
maybe we did try it.
we did try that. It's this thing called like a deep latent Gaussian model. There are nonlinear activation functions. It does well on binarized MNIST, sort of a standard thing for image generation.
Thank you, Dustin.
Sorry, but let's take it offline. It's time for the other speaker now. Let's thank Dave again.